For countless millennia, humanity has anchored its understanding of existence to a definitive beginning. We've carved our myths, our philosophies, and even our science around the notion of a clear genesis, a cosmic timeline stretching from inception to the present, seemingly immutable. But what if the earliest chapters of that grand cosmic narrative, the very moments following the Big Bang, are fundamentally misread? Enter Jade's GS 13-0, a faint crimson smear of light captured by the revolutionary James Webb Space Telescope over 13 billion light-years away. This single, luminous galaxy, observed when the universe was barely a toddler, has torn a gaping hole in our cosmic certainty. This isn't merely an astronomical curiosity, it is a cosmic Rosetta Stone. Its impossible existence hints at a hidden layer of physics, challenging the very pillars of our understanding, from the mysterious nature of dark matter and the formation of the first stars to the precise timeline of the universe itself. We are being compelled to rewrite the most foundational scientific stories of creation. In this documentary, we will journey to the edge of observable time, exploring the groundbreaking discovery of Jade's GS's 13-0. We will unravel why its sheer existence defies our most cherished cosmological models, and how this impossible galaxy is now serving as the ultimate key, forcing scientists to rethink everything from the fundamental properties of dark matter to the astonishing genesis of the very first stars. This is a story that will challenge and expand your perception of cosmic beginnings. If you're ready to witness the universe reveal its most profound secrets, then make sure to subscribe to Terran and hit that notification bell. Prepare yourselves. We begin. To truly, we first need a conduit, an unparalleled instrument capable of capturing the universe's most ancient elusive light. This is where the James Webb Space Telescope, or JWST, enters the cosmic stage. Far more than a mere successor to Hubble, Webb was conceived and engineered as humanity's ultimate time machine, designed to push our observational limits to the very edge of the observable cosmos, and, by extension, the universe's infancy. Its mission was not simply to see farther, but to peer back through time itself, observing the epoch when the first stars ignited and the first galaxies began to coalesce from the primordial darkness. The key to Webb's extraordinary temporal vision lies in its unparalleled sensitivity to infrared light. Unlike the visible light our eyes perceive, or even much of the ultraviolet spectrum Hubble specialized in, infrared radiation carries the faint, stretched echoes of the universe's earliest moments. To understand why, we must grasp the relentless expansion of space. As the cosmos inflates, like a constantly expanding balloon, the light waves traveling across it are stretched along with the fabric of space-time. This phenomenon, known as cosmological redshift, shifts light from shorter, bluer wavelengths towards longer, redder, and eventually infrared wavelengths. The farther away an object, the longer its light has travelled through an expanding universe, and thus the more severely redshifted it becomes. So, the earliest, most distant galaxies appear to us not as brilliant blue youth, but as incredibly faint. Deep infrared embers. Webb's design is a testament to this understanding. Its centerpiece is a colossal gold-coated primary mirror, an 18-segment beryllium mosaic spanning 6.5 meters, more than 6 times the light-gathering area of Hubble's single mirror. This golden aperture is not just for size. The thin layer of gold enhances its reflectivity for infrared light. Each segment is meticulously aligned to within nanometers, creating a single, precise light-collecting surface. This immense chilled eye is positioned a staggering 1.5 million kilometers from Earth at a gravitationally stable point known as L2, the second Lagrange point. This remote, dark vantage offers an unobstructed view of the cosmos, far from the warmth and glare of our home planet and the Sun, which would otherwise overwhelm its delicate infrared detectors. Maintaining an operating temperature below 230 degrees Celsius, just 40 Kelvin above absolute zero, is not merely a technical feat, it is an absolute necessity. At these frigid temperatures, Webb's own instruments emit negligible infrared radiation, preventing them from blinding themselves with their own heat. This extreme cooling, facilitated by a 5-layer tennis court-sized sunshield, ensures that Webb can detect the faint ancient infrared glow of galaxies whose light has journeyed across billions of years of cosmic expansion. Its suite of instruments, including the near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, and the mid-infrared instrument, MIRI, are each specialized to capture and analyze these incredibly faint signals, dissecting the light into its constituent wavelengths to reveal the chemical composition, temperature, and motion of these primordial stellar nurseries. The concept of a telescope as a time machine, while often invoked, finds its most profound realization in Webb. Light, traveling at a finite speed of roughly 300,000 kilometers per second, carries a history lesson with every photon. Every additional light year of distance between us and a cosmic object represents another year into its past. Therefore, when Webb peers more than 13 billion light-years away, it is not merely observing distant space, it is looking 13 billion years into the past, approaching the cosmic precipice of the Big Bang itself. It reveals the universe not as it is now, but as it was in its formative moments, a mere few 100 million years after its birth. It is an evidentiary exhibit of the universe's childhood, delivered directly to our scientific scrutiny. Before Webb, our understanding of this epoch, often dubbed the Cosmic Dark Ages and the subsequent Cosmic Dawn, was largely theoretical, based on extrapolations from the standard cosmological model lambda CDM. This model posits that after the initial fiery Big Bang and the subsequent cooling that allowed the first atoms of hydrogen and helium to form, the universe entered a period of profound darkness. For hundreds of millions of years, there were no stars, no galaxies, only a vast expanse of neutral gas, slowly clumping together under the influence of gravity, guided by the unseen scaffolding of dark matter. Scientists expected the first stars, the population 3 stars, to ignite around 200 million years after the Big Bang, followed by a gradual process of stellar generations enriching the gas with heavier elements, eventually leading to the slow, stately assembly of the first compact galaxies around 500 million to a billion years after cosmic genesis. Hubble, with its visible and ultraviolet capabilities, could only glimpse the fringes of this era, showing us galaxies that were already relatively mature. Webb was designed to fill this observational gap, to capture the missing intermediate stages, to confirm this slow and steady march from gas to galaxy. Astronomers eagerly anticipated witnessing the universe's nascent structures in their chaotic, unrefined youth, validating the painstakingly constructed timeline. Yet, as the first deep-field images began to stream back from L2, showing a patch of sky no larger than a grain of sand held at arm's length, the initial excitement quickly morphed into profound astonishment. The universe's earliest glimmer was not a gentle anticipated dawn, but an astonishingly bright and densely populated landscape. Webb found not just a few fledgling galaxies, but thousands, many of them already surprisingly bright, compact and massive. These findings were not confirmations, they were confrontations, hinting that the universe's evolutionary story had taken a radically different, far faster path than anyone had ever dared to predict. It was in this sea of unexpected complexity that a particular anomaly, Jade's Gest 13.0, would emerge as a pivotal challenge to our entire cosmological framework. End of hook section. Before the revolutionary insights provided by the James Webb Space Telescope, the prevailing understanding of our universe's genesis and early evolution was meticulously codified within the lambda CDM model. This framework, a cornerstone of modern cosmology, describes a cosmos composed primarily of dark energy, which drives its accelerating expansion, cold dark matter and invisible gravitational scaffolding, and ordinary baryonic matter from which all stars, planets and life are forged. According to this standard narrative, the universe began approximately 13.8 billion years ago with the Big Bang, an infinitely hot, dense singularity that rapidly expanded and cooled, setting the stage for all subsequent cosmic history. In the immediate aftermath of the Big Bang, the universe was an opaque incandescent plasma, a superheated soup of elementary particles, so dense that light could not travel freely. Protons and electrons were constantly interacting, preventing photons from escaping. This primordial fog persisted for approximately 380,000 years, a fleeting moment in cosmic terms, but an eternity for the nascent universe. As space expanded, this plasma cooled, eventually reaching a critical temperature where electrons could finally combine with protons to form the first neutral hydrogen atoms, and with helium nuclei to form neutral helium. This pivotal event, known as recombination, allowed photons to decouple from matter, streaming freely across the cosmos for the first time. The residual glow of this ancient light, stretched and cooled by billions of years of expansion, is what we now detect as the cosmic microwave background, or CMB, a faint, omnipresent echo of the universe's luminous infancy. Following the clarity of recombination, the universe plunged into a profound epoch known as the Cosmic Dark Ages. This was not a period of literal darkness, but rather an absence of brilliant concentrated light sources. The cosmos was filled primarily with diffuse, neutral hydrogen and helium gas, interspersed with the elusive, invisible tendrils of cold dark matter. There were no stars, no galaxies, and therefore no new light beyond the fading afterglow of the CMB. This was a quiescent, featureless expanse, a vast, uniform cosmic ocean devoid of the vibrant structures we recognize today. This era was expected to persist for hundreds of millions of years, a long, quiet interval of gravitational slumber. Within this quiet darkness, however, the seeds of future complexity were slowly germinating. The subtle density fluctuations imprinted on the universe during an even earlier inflationary period began to exert their influence. Gravity, the inexorable architect of cosmic structure, started to amplify these tiny irregularities. Crucially, it was dark matter that provided the initial gravitational framework. Unlike ordinary matter, dark matter does not interact with light or other forces, only gravity. Therefore, it could clump together much earlier and more efficiently, forming dense halos or gravitational wells that acted as invisible lures for the more diffuse baryonic gas. This hierarchical process dictated that the larger structures would form first, slowly accumulating matter. As these dark matter halos grew, they gradually drew in the neutral hydrogen and helium gas, compressing it to ever greater densities. Eventually, in the most massive and densest of these clumps, the gas became sufficiently concentrated and heated for nuclear fusion to ignite. This marked the birth of the universe's very first stars, hypothesized to be the legendary Population 3 stars. These primordial suns were unlike any stars we see today. Formed purely from hydrogen and helium, without any heavier elements, they were predicted to be truly gargantuan, hundreds, even thousands of times the mass of our own sun. Burning with incredible ferocity and temperatures, their lifespans were incredibly brief, perhaps only a few million years. Yet, their importance cannot be overstated. They were the universe's first light sources, the true harbingers of the cosmic dawn, expected to appear. The violent demise of these colossal Population 3 stars, exploding as hypernovae, played a critical role in shaping the subsequent universe. These cataclysmic events seeded the surrounding pristine gas with the first metals, astronomers' shorthand for any element heavier than hydrogen and helium. Elements like carbon, oxygen, nitrogen, and iron, crucial for planet formation and life, could only be forged in the fiery hearts of stars and dispersed through supernova explosions. This process of chemical enrichment was fundamental because these heavier elements act as efficient coolants for gas clouds. Gas-containing metals can radiate energy away more effectively, allowing it to collapse more readily into subsequent generations of stars and, eventually, into more complex structures like galaxies. This continuous cycle of star formation, death, and enrichment was expected to be a gradual, time-consuming affair. Each generation of stars had to live, die, and disperse its heavy elements before the next, more metal-rich generation could form. Therefore, the formation of the first organized galaxies, cohesive structures containing billions of stars, was envisioned as a slow, stately dance of gravity and gas. Initial proto-galaxies, small and chaotic, would slowly merge and accrete more matter, growing in size and complexity over hundreds of millions, even billions of years. Cosmological simulations based on the Lambda CDM model consistently predicted that mature, luminous galaxies, comparable in size to the Milky Way, would only become prevalent around 1 billion years after the Big Bang. This period of burgeoning star and galaxy formation also initiated the epoch of rionization. The intense ultraviolet radiation emitted by the first population of 3 stars and early galaxies began to strip electrons from the neutral hydrogen atoms that filled the universe, gradually transforming the opaque cosmic fog back into a transparent ionized plasma. This process was thought to unfold gradually, taking several 100 million years, starting roughly 500 million years after the Big Bang and completing around 900 million years. It was a slow lifting of the cosmic veil, allowing light to travel unimpeded across vast distances, illuminating the structures that gravity had slowly sculpted. For decades, this intricate narrative of cosmic evolution, from the Big Bang's plasma to the first stars and the gradual assembly of galaxies, stood as our most robust scientific consensus. Observatories like the Hubble Space Telescope, while incapable of seeing the very first light due to its infrared limitations, largely confirmed the later stages of this timeline, observing increasingly young, less evolved galaxies the farther it looked. The picture painted was one of a universe that began simply and evolved with a measured, predictable pace, slowly building its grandeur from fundamental components. This was the script that the James Webb Space Telescope was sent to verify and deepen, to observe those missing early stages. However, what it found instead was a universe that had apparently skipped several acts, revealing a startlingly complex and mature cosmos far earlier than anyone had ever thought possible, thrusting JD's G13-0 into the spotlight as an undeniable challenge to this long-held cosmic narrative. The James Webb Space Telescope, poised at its L2 outpost, was designed to confirm the slow, majestic unfolding of the cosmos as prescribed by the Lambda CDM model. It was meant to be the ultimate historical scribe, carefully documenting the transition from the cosmic dark ages to the cosmic dawn, observing the first flickering lights and the gradual assembly of nascent galaxies. Yet, from its very first deep field observations, Webb did not merely confirm, it confronted. Its initial data streams presented not the expected chaotic smudges of fledgling stellar systems, but rather a bewildering abundance of surprisingly bright, well-formed galaxies, pushing the boundaries of what was thought possible in the early universe. Among these startling revelations, one particular object, JD's GSS-0, emerged as the prime anomaly, a beacon of impossible light in the universe's infancy. Discovered within the JWST Advanced Deep Extragalactic Survey, JADES, program, this faint crimson smear appeared in images captured by Webb's near-infrared camera. Its colour, stretched to extreme infrared wavelengths, immediately signalled its immense distance. Through meticulous spectroscopic analysis, astronomers measured its redshift, a staggering Z-Sunna 13.2. This numerical value, far from being an abstract scientific datum, is a direct portal to the past, indicating that the light from JD's GS-Z13-0 began its journey towards us when the universe was only approximately 320 to 330 million years old. To truly grasp the profound implication of this age, consider the sheer scale shift. The universe, in its entirety, is about 13.8 billion years old. JADE's GS-Z13-0 existed when the cosmos was barely 2.3% of its current age, a mere blink in cosmic time. Imagine a human infant, barely 2 years old, already exhibiting the physical and intellectual maturity of a fully grown adult. That is the observational equivalent of what Webb found. According to the Lambda CDM model, a galaxy forming at such an early epoch should be small, chaotic, and actively accreting gas, perhaps a loose collection of the very first pristine population 3 stars, still in their initial stages of organization. It certainly should not be a luminous, compact, and seemingly mature stellar system. Yet, JADE's GS-Z13-0 appeared undeniably luminous and remarkably compact, suggesting a significant stellar mass already in place. Its brightness implies a prodigious rate of star formation, an efficiency in converting primordial gas into stars that drastically outpaces what our models predict for that cosmic epoch. We are talking about a galaxy that, by all accounts, appears to have accumulated hundreds of millions, possibly even a billion, solar masses of stars in a time frame that allows for only a handful of stellar generations at best. The standard simulations, which meticulously trace the gravitational collapse of dark matter and the subsequent infall of baryonic gas, simply cannot reproduce such rapid assembly. They consistently predict that galaxies of comparable size and luminosity require nearly 1 billion years to grow, patiently coalescing matter over vast stretches of cosmic time. The very existence of JD's GS Z13-0, therefore, presents a direct, unequivocal challenge to the fundamental tenets of our standard cosmological understanding. It is an impossible galaxy, because its characteristics fundamentally contradict the expected pace of cosmic evolution. Its maturity, its luminosity, its sheer stellar content, all conspire to suggest a universe that was building complex structures far faster and more efficiently than the prevailing scientific narratives allow. This isn't a minor discrepancy, it's a profound pattern. Break, forcing cosmologists to confront the possibility that either their models are incomplete or the physics governing the early universe operated under entirely different, more dynamic rules. This paradox, far from being a scientific dead end, transforms JD's GZ13-0 into a veritable Rosetta Stone for cosmology. Its defiance of expectation makes it an invaluable clue, a singular data point that can unlock deeper truths about the universe's foundational mechanics. If a galaxy this evolved could exist so early, it compels us to ask, what fundamental assumptions about cosmic growth are we missing? Could the unseen scaffold of dark matter have behaved differently, clumping more aggressively or interacting in ways we hadn't conceived? Or perhaps the processes of star formation themselves were far more intense, more violent, and more efficient in the universe's youth, accelerating the creation of heavy elements and subsequent stellar generations. The implications of JD's GS Z13-0 extend far beyond merely adjusting a timeline. It forces a radical re-evaluation of the earliest cosmic conditions and the forces at play. This single, distant galaxy has become the focal point of an intense scientific investigation, probing the very nature of dark matter, the invisible glue of the cosmos, and the intricate mechanisms that ignited the first stars. It challenges us to not just observe the universe, but to truly understand the hidden physics woven into the fabric of reality, pushing the boundaries of human knowledge and redefining what we consider possible in the grand narrative of cosmic creation. It's a compelling intellectual crisis, a cosmic detective story, where an impossible exhibit demands a new understanding of the very laws of physics. The astounding luminosity and apparent maturity of JD's GS Z13-0 and other similar early galaxies detected by Webb are not just surprising. They present a profound chemical enigma. Their very existence forces us to confront a critical aspect of galactic evolution, the process of chemical enrichment, or the creation and dispersal of elements heavier than hydrogen and helium. In astronomical parlance, these heavier elements are collectively termed metals. The presence or absence of these metals acts as a cosmic clock, providing invaluable clues about a galaxy's age and the history of star formation within it. To appreciate this, we must first recall the pristine composition of the early universe. Cosmos was a remarkably simple place, chemically speaking. It consisted almost entirely of hydrogen, about 75%, and helium, about 25%, with only trace amounts of lithium. These are the elements that formed during the Big Bang nucleosynthesis, the brief period of intense heat and density when the universe was only minutes old. There were no carbon, no oxygen, no nitrogen, no iron. None of the elements essential for rocky planets, complex chemistry, or life itself. These fundamental building blocks had to be forged in the nuclear furnaces of stars. The very first stars, the theoretical population 3 stars, formed solely from this primordial blend of hydrogen and helium. Without any heavier elements to aid in cooling, these protostars would have needed immense masses to overcome internal pressures and ignite fusion. As we discussed, they are theorized to have been hundreds of times the mass of our Sun, burning incredibly hot and bright, with extremely short lifespans of only a few million years. These giants then met their end in spectacular fashion, exploding as supernovas or even hypernova. It is during these cataclysmic events, and in the advanced fusion stages within these massive stars, that the first heavier elements were synthesized and subsequently blasted out into the surrounding interstellar medium. This process of stellar birth, death, and elemental dispersal is crucial. Once these first supernovae occurred, the expelled metals enriched the pristine gas clouds. These heavier elements act as efficient coolants. They can radiate energy away more effectively than pure hydrogen and helium. This enhanced cooling allows subsequent generations of gas clouds to collapse more easily and form new stars. These second-generation stars would therefore contain a higher proportion of metals, and their own eventual deaths would further enrich the cosmos, creating a continuous cycle of chemical evolution. Each successive generation of stars and galaxies would thus become progressively more metal-rich. The key to the enigma of JD's GS-Z13 lies in this cycle. When Webb's near-infrared spectrograph, NIRSpec, analysed the light from these extraordinarily distant galaxies, it wasn't just measuring their redshift, it was also dissecting their chemical fingerprints. The spectrograph breaks down the incoming light into its constituent wavelengths, revealing distinct spectral lines, specific colours of light that are absorbed or emitted by particular elements. The presence of these lines acts as an undeniable signature, betraying the chemical composition of the distant galaxy, and what Webb found was truly astonishing. The spectra of JD's GS-0 and other similarly ancient galaxies showed clear, unmistakable traces of elements like oxygen, neon, and even carbon. These are not primordial elements, they are products of stellar nucleosynthesis. Oxygen, for example, is primarily created in massive stars and dispersed through supernovae. Carbon is essential for organic molecules and typically requires at least a second generation of stars to be produced in significant quantities. The detection of these metals in galaxies that existed only 250 to 350 million years after the Big Bang implies an extraordinarily rapid pace of chemical enrichment. Consider the scale shift involved. For a significant amount of oxygen or carbon to be present in JD's GS-13 several complete stellar life cycles must have already occurred. The first generation of population 3 stars would have had to form, live out their brief lives, and explode. Then, the enriched gas would have had to cool and collapse to form a second generation of stars, which in turn would need to live and die, potentially seeding the environment for a third. All of this in a mere few 100 million years. For perspective, our Sun is a relatively metal-rich, population the 1 star, and it is 4.6 billion years old, having formed from gas clouds already enriched by countless previous stellar generations. The Milky Way has been steadily accumulating metals for over 13 billion years. The timeline implied by JD's GS-Z13 chemical composition is breathtakingly compressed. It suggests that the first stellar populations must have formed, evolved, and dispersed their heavy elements with astonishing efficiency and speed, possibly within the first 100 to 200 million years of the universe's existence. This challenges our models of stellar evolution and galaxy formation, which typically assume a more gradual, less efficient process of chemical buildup. It hints at a very different early cosmos, one where the creation of elements, and thus the potential for subsequent complexity, was accelerated to an almost unimaginable degree. This rapid chemical enrichment is not just a detail, it's a fundamental challenge to the slow and steady narrative of the cosmic dawn. It paints a picture of a young universe that was a true cosmic furnace, where star formation was not a gentle sunrise, but a series of violent, efficient bursts of creation, recycling matter at an unprecedented rate. The sheer density of elements like oxygen and carbon in JD's GS-Z13 acts as an evidentiary exhibit, demanding that we reconsider the mechanisms by which the universe first built its atomic diversity, ultimately paving the way for the complex chemistry that governs all observable matter today. This deepens the mystery of JD's GS-Z13 and transforms it from a simple distant light into a profound indicator of early cosmic dynamism. When faced with such extraordinary claims, galaxies seemingly too old, too luminous, and too chemically evolved for their epoch, the scientific community does not simply accept them at face value. Instead, an intense period of scrutiny, cross-verification, and meticulous astronomical due diligence begins. This rigorous process is fundamental to the scientific method, especially when observations challenge long-established paradigms. For JD's GS-Z13 and its equally perplexing companions, this meant subjecting the James Webb Space Telescope's initial findings to an exhaustive battery of checks and re-evaluations. The first line of skepticism often centers on the most critical parameter, distance. A galaxy's apparent age is derived directly from its redshift, which in turn is a measure of how much its light has been stretched by the universe's expansion. If the redshift measurement were inaccurate, or if the object were not as far away as initially calculated, then its anomalous nature would vanish. For instance, a closer galaxy, heavily obscured by dust, could appear redder, mimicking the high redshift signature of a truly distant object. This dust reddening effect is a well-known pitfall in observational astronomy. To counteract this, independent research teams around the globe, often utilizing different data processing pipelines and calibration methods, began to re-examine the raw data from Webb. They employed a variety of photometric techniques, analyzing the galaxy's brightness across multiple infrared wavelengths. This multi-band approach helps to distinguish between genuinely high redshift objects and dust-reddened imposters. A truly distant galaxy will show a characteristic break in its spectrum at specific wavelengths due to the absorption of light by neutral hydrogen in the intervening cosmos, a signature that dust reddening cannot replicate. Crucially, the ultimate arbiter of a galaxy's redshift and chemical composition is spectroscopy. While photometry provides a broad estimate of distance, spectroscopy offers a precise measurement of spectral lines, the unique fingerprints of elements. Webb's near-infrared spectrograph, NIRSpec, is a marvel of engineering designed precisely for this task. By dispersing the incoming light into a rainbow-like spectrum, NIRSpec can identify specific emission or absorption lines, particularly the Lyman alpha line of hydrogen, which is profoundly shifted into the infrared for these ancient galaxies. The precise wavelength of this shifted line directly translates into an accurate redshift value. When the NIRSpec data for JD's GS Z13-0 and several other candidates were meticulously analysed, the results were unequivocal. The distinctive hydrogen emission lines were measured with high precision, confirming their extreme redshifts and thus their immense distances. These objects were indeed more than 13 billion light-years away, observed as they existed only a few 100 million years after the Big Bang. This robust spectroscopic confirmation largely ruled out the simpler explanations, such as dust reddening, as the primary cause for their unusual appearance. The galaxies were genuinely ancient. Another potential confounder is gravitational lensing. Massive galaxy clusters or dark matter clumps positioned between us and a distant galaxy can act like cosmic magnifying glasses, bending and amplifying the light from background objects. This phenomenon can make intrinsically small, faint galaxies appear much brighter and larger, potentially leading to an overestimation of their true stellar mass and maturity. While gravitational lensing can be a powerful tool for studying incredibly faint objects otherwise invisible, it can also complicate the interpretation of their intrinsic properties. Astronomers rigorously assessed the possibility of strong gravitational lensing for JD's GS Z13-0. They mapped the distribution of matter, both visible and dark, in the foreground regions along the line of sight to the galaxy. In some cases, faint distant galaxies indeed benefit from a modest amount of gravitational magnification. However, for the most striking anomalies like JD's GS Z13-0, the observed luminosity and inferred mass were simply too high to be explained away by lensing alone. Even accounting for a reasonable amount of magnification, the intrinsic properties of these galaxies remained profoundly challenging to the standard models. Their light was simply too bright, their chemical signatures too evolved, for the short time elapsed since the Big Bang. Furthermore, the sheer number of these anomalous galaxies discovered in Webb's early deep fields became a statistical challenge in itself. If JD's GS Z13-0 were a singular outlier, it might be dismissed as an exotic, rare event. But Webb's comprehensive surveys, such as the JD's program itself and the GLASS, Grism Lens Amplified Survey from Space program, revealed not one, but dozens of these surprisingly bright and massive galaxies at extreme redshifts. The statistical prevalence of these objects in the early universe, far exceeding predictions, cemented the notion that something fundamental about cosmic evolution was indeed misunderstood. The collective evidence from multiple independent observations, confirmed by rigorous spectroscopic measurements and careful consideration of potential biases, painted an undeniable picture. The infant cosmos was teeming with mature galaxies that, according to prevailing theory, should not have existed so early. This meticulous astronomical due diligence, far from debunking the initial surprising findings, instead strengthened them. It transformed JD's GS13-0 from a tantalizing anomaly into a robust evidentiary exhibit, a concrete observation demanding a recalibration of our cosmic understanding. It shifted the scientific question from "is this real?" to "how is this possible?" The implications were clear. The universe had built its complex structures with a speed and efficiency that defied the established narrative, compelling cosmologists to embark on an urgent quest to revise their models of dark matter, star formation, and the very timeline of cosmic history. The impossible galaxy had been confirmed, and now the real work of decoding its message could begin. The verified existence of galaxies like JD's GS Z13, brimming with stars and heavy elements in the universe's infancy, cast a stark spotlight on one of cosmology's most persistent enigmas: dark matter. This invisible, mysterious substance, making up approximately 85% of all matter in the cosmos, is the unseen architect of cosmic structure. According to the lambda CDM model, dark matter provides the gravitational scaffolding upon which ordinary baryonic gas slowly condenses to form stars and galaxies. However, the rapid assembly observed in JD's GS Z13 suggests that this scaffolding might have behaved in ways more dynamic and efficient than previously assumed, potentially leading to a radical reshaping of our understanding of this elusive cosmic component. In the conventional picture, cold dark matter, CDM particles, are thought to be weakly interacting, moving slowly and only engaging through gravity. They form dense halos, which then attract and funnel ordinary gas, allowing it to cool and collapse into stars. This process, while elegant, is inherently gradual. Simulations based on the CDM paradigm typically show a hierarchical build-up, where small clumps form first and then merge over billions of years to create larger structures. The problem is, JD's GSE Z13 appears to have bypassed much of this slow choreography, emerging fully formed in a mere fraction of the time predicted. This implies that the dark matter scaffolding must have either formed denser clumps much faster or been far more effective at drawing in gas. One compelling hypothesis now being explored by physicists is that dark matter might not be entirely cold or non-interacting in the way we've assumed. What if dark matter particles, instead of merely passing through each other, possess some form of self-interaction? This concept, known as self-interacting dark matter, SIDM, proposes that dark matter particles can occasionally collide and scatter off one another, much like billiard balls. Such interactions, even if rare, could have profound consequences for the distribution of dark matter within galactic halos. Instead of forming diffuse extended halos, SIDM could allow dark matter to clump together more efficiently and form denser cores in the centers of early galaxies. These denser dark matter cores would create significantly deeper gravitational wells, acting as much more powerful attractors for primordial gas. This intensified gravitational pull could have accelerated the unveil of gas, compressing it to the critical densities needed for rapid star formation much earlier than standard models allow. Essentially, a small change in how dark matter interacts with itself could have ignited a cascade of structure formation, providing the necessary boost to explain the precocious galaxies Webb observes. It transforms dark matter from a passive framework into a more active, dynamic participant in early cosmic evolution, demanding changes to our particle physics models. Another intriguing possibility involves fuzzy dark matter. This theoretical construct posits that dark matter particles are not point-like particles at all, but incredibly light wave-like entities, perhaps even ultralight bosons. At cosmic scales, these waves would behave classically, forming gravitational halos. However, at galactic scales, their quantum wave nature would become significant. Instead of forming sharp, distinct clumps, fuzzy dark matter would create a quantum pressure that smears out the smallest structures, but could also lead to a different collapse dynamic. Some models suggest that this wave-like nature could lead to a more efficient collapse of gas into stars within larger halos, effectively accelerating the galaxy formation process. This represents a radical departure from the standard cold dark matter model, and would require a completely new understanding of the fundamental nature of this invisible constituent of the universe. Furthermore, some theorists are even speculating about temporary interactions between dark matter and radiation in the extremely hot, dense early universe. While dark matter is generally considered to be decoupled from ordinary matter and radiation, a fleeting interaction in the universe's first moments perhaps through an exotic force carrier, could have created density fluctuations that were much stronger than previously calculated. These enhanced fluctuations would have provided much deeper gravitational seeds for both dark matter and baryonic matter to fall into, almost instantly creating the conditions for rapid galaxy formation. Such a scenario would imply entirely new physics beyond the standard model of particle physics, linking the microworld of quantum interactions to the macroworld of galaxy formation. The challenge posed by JD's GS-Z13 is not just about modifying existing parameters, it's about exploring entirely new physical mechanisms for dark matter. The impossible galaxy suggests that dark matter, far from being a simple, inert scaffolding, might be a complex, multifaceted entity with properties we're only just beginning to uncover. New simulations are now being developed, incorporating these more exotic dark matter models and using Webb's early data as a crucial benchmark. The goal is to see if any of these alternative dark matter scenarios can reproduce the observed abundance and maturity of early galaxies, thereby transforming JD's GZ13 from an anomaly into a key piece of evidence for a new understanding of the universe's primary gravitational architect. This exploration is pushing the boundaries of both astrophysics and particle physics, forging new interdisciplinary connections in the grand quest to understand cosmic origins. Beyond the re-evaluation of dark matter's role, the precocious nature of galaxies like JD's GS-Z13 also compels us to scrutinize the very engine of cosmic creation, star formation itself. If these galaxies amassed billions of stars and significant heavy element content in just a few 100 million years, the processes by which primordial gas transformed into stellar nurseries must have been far more efficient and intense than previously conceived. This implies a radical departure from the slow and steady model of stellar genesis, painting a picture of an early cosmos that was a veritable hyperfurnace of creation. The standard model of star formation, even in the modern universe, is a complex dance of gravity, gas dynamics, and feedback mechanisms. Giant molecular clouds, vast reservoirs of gas and dust, slowly collapse under their own gravity. As they contract, they fragment into smaller, denser cores that eventually ignite as new stars. This process, however, is notoriously inefficient. In typical star-forming regions like the Orion Nebula, only a small percentage of the available gas actually turns into stars over millions of years. The rest is either blown away by stellar winds and supernova feedback, or remains too diffuse to collapse. Yet, to explain JD's GS-Z13, we need to envision a scenario where gas clouds converted their mass into stars with near-perfect efficiency, almost instantaneously. One radical idea, already hinted at by the chemical enigma, involves the properties of the very first stars, the population 3 stars. If these primordial suns were not merely, but perhaps thousands of times larger, their impact would be proportionally amplified. Such supermassive population 3 stars would burn with an unimaginable intensity, consuming their fuel at a furious rate. Their lifespans would be incredibly short, perhaps just a few million years, culminating in hypernovae explosions that would inject massive amounts of heavy elements into the surrounding medium in a remarkably short cosmic timescale. These rapid-fire explosions would not only enrich the gas far faster, but their powerful shock waves could also trigger subsequent waves of star formation, compressing nearby gas clouds and initiating new stellar generations with breathtaking speed. This cascading effect could explain the rapid succession of stellar populations needed to account for the observed metallicity in JD's GS-Z13. Another scenario involves the direct collapse of immense primordial gas clouds. In the early universe, before significant metal enrichment, gas clouds had fewer ways to cool efficiently. However, if a truly massive cloud, perhaps millions of solar masses, accumulated rapidly within an exceptionally deep dark matter halo, it might collapse gravitationally without fragmenting into smaller stars. Instead, the entire cloud could directly collapse into a single, supermassive object, perhaps even a supermassive black hole seed, which would then rapidly accrete surrounding gas and ignite intense starburst activity in its vicinity. This direct collapse model could explain both the rapid formation of a significant stellar mass and the early appearance of supermassive black holes, which we will discuss further. The early universe might also have been characterized by incredibly violent and frequent galaxy mergers. As dark matter halos formed and grew, they would inevitably draw in smaller clumps, leading to frequent collisions between nascent galaxies. These galactic mergers are known to be powerful drivers of star formation in the modern universe, as the shock waves and tidal forces compress gas clouds, triggering intense bursts of stellar creation, often called starbursts. In the crowded, turbulent environment of the early cosmos, these mergers could have been far more commonplace and energetic, acting as cosmic pressure cookers that rapidly converted vast quantities of gas into stars. Imagine colliding rivers of gas, compressed to the point of ignition, flaring briefly like cosmic fireworks before settling into more stable configurations. This would explain the observed luminosity and compactness of JD's GS-Z13-0. It might be the remnant of such a hyper-efficient starburst triggered by an early galactic collision. Webb's observations indeed suggest star formation rates in these early galaxies that are up to 100 times greater than those seen in the Milky Way today. Such intense rates imply that these galaxies were not just slowly gathering stars, but were undergoing periods of explosive, almost simultaneous star formation across their entire volume. This kind of extreme efficiency necessitates a reconsideration of the physics of gas cooling, turbulence, and gravitational stability in the early universe. Perhaps the pristine, metal-poor gas of that era, while less efficient at radiating heat through atomic transitions, was more prone to gravitational instability under the right conditions, allowing it to collapse into stars with fewer impediments. The challenge for theorists now is to construct simulations that can reproduce these astonishing rates of star formation within the incredibly short cosmic timeline. These models must incorporate mechanisms that dramatically boost both the rate of gas collapse and its conversion into stars by factors of 10 or more compared to conventional simulations. This often involves fine-tuning parameters related to the initial density fluctuations, the behavior of dark matter, and the feedback processes from early stars and black holes. The engine of creation in the early universe, as illuminated by JD's GS-Z13-0, was clearly operating at a fundamentally higher gear, pushing the limits of our understanding of stellar genesis and galactic growth. This isn't merely an adjustment to a formula, it's an exploration into a potentially more violent, more efficient, and ultimately more awe-inspiring cosmic dawn than we ever conceived. As if the precocious galaxies and their rapid stellar formation weren't enough to challenge cosmological orthodoxy, the James Webb Space Telescope delivered yet another profound surprise, compelling evidence for the early reign of supermassive black holes. These colossal gravitational behemoths, millions or even billions of times the mass of our Sun, were once thought to be products of gradual evolution, growing slowly over billions of years at the hearts of mature galaxies. However, Webb's deep field observations, including those of JD's GS-13-0 and other ancient systems, reveal a universe where these cosmic leviathans were already in place, astonishingly massive and fiercely active, hundreds of millions of years earlier than our models predicted. In the modern universe, supermassive black holes reside at the centre of almost every large galaxy, including our own Milky Way's Sagittarius A. Their growth is typically attributed to two primary mechanisms. First, the slow, steady accretion of gas and dust from their galactic surroundings, and second, through mergers with other black holes during galactic collisions. Both processes are thought to be time-intensive, requiring ample cosmic epochs to accumulate such immense mass. The observed masses of these early black holes, some already reaching millions or even billions of solar masses when the universe was less than 500 million years old, simply do not fit within this established framework. The timeline leaves insufficient room for them to have grown from smaller stellar remnant black holes, those formed from the collapse of massive stars through conventional accretion. This fundamental discrepancy has propelled the concept of direct collapse black holes to the forefront of theoretical astrophysics. This radical hypothesis suggests that under the extreme conditions of the early universe, certain primordial gas clouds, perhaps millions of times the mass of the Sun, might have collapsed directly into a black hole without first forming stars. Such an event would require very specific conditions, a super-dense pocket of gas, often within an exceptionally deep dark matter halo, that is prevented from cooling too efficiently and fragmenting into smaller stellar objects. if the gas remains hot enough to resist fragmentation, its immense mass could collapse almost in a single go, forming a seed black hole that is already thousands or tens of thousands of solar masses. These primordial, or direct collapse black hole seeds would then have a significant head start, allowing them to accrete gas at an extraordinarily rapid rate, growing into supermassive black holes in a fraction of the time required by conventional growth models. The dense environment of the early universe, with abundant pristine gas, would provide the perfect cosmic buffet for these ravenous young black holes. Their intense gravitational pull would draw in vast quantities of surrounding gas, heating it to extreme temperatures and causing it to emit copious amounts of X-rays and other high-energy radiation, making them incredibly luminous and detectable even across billions of light-years. Webb's observations lend tantalizing support to this direct collapse scenario. Many of the compact, intensely bright sources detected in the deep fields exhibit light patterns consistent with actively feeding supermassive black holes, known as quasars or active galactic nuclei, AGN. Their spectra show broad emission lines, indicating gas moving at extreme velocities, a hallmark of material spiraling into a massive black hole. Intriguingly, some of these ultra-luminous sources appear to be smaller than expected for their brightness, suggesting a highly compact, super-efficient engine at their core, exactly what one would expect from a rapidly growing direct collapse black hole. The presence of these early massive black holes suggests that the universe had a very efficient mechanism for creating these monstrous objects almost from the beginning. Furthermore, the early reign of supermassive black holes introduces a critical feedback loop into early galaxy formation. The intense radiation and powerful jets emanating from these active black holes could have had a profound impact on their host galaxies. Far from being passive residents, these black holes could have stirred, heated, or even expelled vast quantities of gas from their galactic nurseries. This feedback mechanism could regulate star formation, preventing galaxies from converting all their gas into stars too quickly, or conversely, in some scenarios, compressing gas to trigger intense starbursts. In this complex, intimate partnership, galaxies and their central black holes appear to have co-evolved from the very earliest epochs, shaping each other's growth and the entire cosmic landscape. The discovery of these ancient monsters by Webb is not just an observational triumph, it's a critical piece of the JADES GSS 30 puzzle. The rapid growth of a supermassive black hole could, in turn, explain the rapid assembly of its host galaxy. A deep gravitational well at the centre, combined with the energy output from an active black hole, might have significantly accelerated the infall of gas and the rate of star formation around it. Thus, understanding how these early supermassive black holes formed and grew has become one of Webb's defining objectives, linking this impossible galaxy to the grander narrative of how the universe built its most extreme structures. It pushes us to consider a universe where the most destructive objects are also, paradoxically, some of the most crucial architects of cosmic evolution, present and powerful from the very dawn of time. The profound revelations from the James Webb Space Telescope, exemplified by the existence refining our models of dark matter and star formation. These discoveries are forcing cosmologists to consider more radical implications, pushing the boundaries of the standard lambda CDM model and even challenging our fundamental understanding of cosmic time and the laws that govern the universe's earliest moments. If galaxies like JADES GSS 13 formed so quickly, it begs the question, is our cosmic timeline itself accurate, or are we glimpsing a deeper layer of physics woven into the very fabric of reality? One immediate area of scrutiny involves the universe's expansion history. The age we assign to a distant galaxy is intricately linked to how much its light has been stretched, or redshifted, by the expansion of space. This calculation relies on an assumed steady rate of cosmic expansion since the Big Bang, but what if that rate wasn't perfectly uniform? If the early universe expanded even slightly faster or slower than our current models predict, our distance and time calculations could be subtly off. A faster early expansion, for instance, would make distant galaxies appear older than they truly are, potentially closing some of the age gap for objects like JADES GS Z0. While current adjustments to the expansion rate cannot entirely resolve the mystery of these overmassive early galaxies, the Webb data certainly adds pressure to the ongoing Hubble tension, a persistent discrepancy between expansion rates measured in the nearby universe and those inferred from early universe observations like the cosmic microwave background. Webb's results may well hold crucial clues to resolving this long-standing cosmological conflict. Beyond simple adjustments, some theories propose a more fundamental deviation from the standard cosmic timeline. What if the geometry of space itself isn't perfectly flat as often assumed? Subtle curvature could alter our measurements of distance and time, making distant objects appear different from what we expect. Or more radically, perhaps the strength of dark energy, the mysterious force accelerating cosmic expansion today, was not constant throughout cosmic history. Some cosmologists are exploring models where dark energy was weaker in the early universe, allowing gravity to more effectively pull matter together and accelerate structure formation, only to strengthen later on and drive the current accelerating expansion. This would represent a significant shift in our understanding of the universe's dominant energy component. Then there are theories that venture into truly speculative territory, challenging the very notion of a singular Big Bang as the ultimate genesis. Near the universe's origin, the known laws of physics merge into a domain where quantum mechanics and general relativity, our two most successful but incompatible theories, must somehow coexist. This realm of quantum gravity is where our understanding falters. Some theorists propose that time itself might have flowed differently in the universe's earliest moments, perhaps thickening as space expanded. Under such exotic conditions, what we measure as 300 million years could have passed in a fraction of that duration, according to the universe's own fundamental clock. This would effectively give galaxies like JD's GS Z13-0 more effective time to form, without violating the apparent cosmic age. Even more audacious are the bouncing universe, or cyclic universe theories. In this view, our universe is not a unique one-off event born from a singularity, but rather the latest iteration in an eternal cycle of expansion and contraction. An earlier cosmos might have collapsed under its own gravity, compressed into a state of maximum density, a big crunch, and then rebounded into a new expansion, our current Big Bang. Such a model could leave faint but detectable imprints, density patterns or relic particles that could have acted as seeds for galaxies, accelerating their formation in the subsequent cycle. If any trace of such a pre-existing cycle could be found in Webb's data, perhaps in extremely uniform patterns or specific gravitational wave signatures, it would fundamentally redefine our concept of a cosmic beginning itself, transforming the Big Bang from an absolute origin into a colossal transition. These radical ideas are not idle speculation. They are driven by the profound observational challenge posed by Webb's data. JD's GS Z13-0 is not just an old galaxy. It's a paradox dramatized, an intellectual crisis for our established cosmological framework. It highlights that something fundamental appears to be missing from our equations of the early cosmos. The universe, in its infancy, was either far more efficient at building structures than our current laws allow, or our laws themselves are incomplete, failing to describe the extreme conditions of creation. The quest to resolve these fundamental questions is pushing theoretical physics into new frontiers. Cosmologists are now building new simulations that incorporate modified gravity, exotic forms of dark matter, and speculative initial conditions. They are blending quantum gravity mathematics with large-scale simulations, attempting to bridge the gap between the smallest fundamental particles and the largest cosmic structures. Webb's precise measurements of early galaxy distribution, their chemical compositions, and the presence of supermassive black holes are providing the crucial benchmarks against which these new, more radical theories are being tested. The impossible galaxy has thus become a crucial catalyst, urging us to explore entirely new physics and potentially rewrite the very foundational laws that govern our universe and its origin. It's a testament to the power of observation to shatter complacency and ignite profound scientific revolutions. The monumental challenge posed by JD's GS Z13-0 and the multitude of other precocious galaxies discovered by the James Webb Space Telescope has ignited a new era of collaborative scientific inquiry. This isn't just about Webb's data. It's about a coordinated, multi-pronged effort across the global scientific community to unlock the universe's deepest secrets. The quest to understand how complexity arose so rapidly in the early cosmos requires a blend of advanced observational technology, sophisticated theoretical modeling, and innovative data analysis techniques. This is the next horizon of cosmology, a grand endeavour to reconstruct the universe's true genesis, photon by photon, equation by equation. Astronomers are now developing an entirely new generation of analytic tools to fully exploit Webb's unprecedented data archive. Machine learning algorithms, for instance, are being trained on thousands of simulated universes, each built with slightly different physical laws or initial conditions. These AI systems then compare these simulated realities with Webb's real observations, searching for the subtle patterns, the hidden faint galaxies, and the unique spectral signatures that best reproduce what Webb sees. This allows researchers to quickly test a vast parameter space, identifying which theoretical frameworks align most closely with the observed universe, and pinpointing where our current models fall short. These algorithms are even beginning to find objects so faint and distant that they stretch the very limits of Webb's detection capabilities, suggesting that the early universe might be even busier and more complex than we can yet confirm with human analysis alone. On the theoretical front, cosmologists are pushing the boundaries of computational astrophysics. New, higher-resolution simulations are being developed, designed to incorporate the more radical ideas sparked by Webb's data. These include models for self-interacting or fuzzy dark matter, scenarios involving direct collapse black hole formation, and even modified gravity theories. The goal is to build comprehensive simulations that can accurately trace the evolution of structure, from the quantum fluctuations of the Big Bang to the formation of galaxies like JD's GS Zia 13-0. This often involves blending the abstract mathematics of quantum gravity with the large-scale dynamics of general relativity, bridging the immense gap between the smallest particles and the largest cosmic structures. Crucially, Webb is not operating in isolation. A fleet of complementary observatories, both current and future, are joining the effort, each providing a unique piece of the cosmic puzzle. Radio telescopes, such as LOFAR in Europe, and the upcoming Square Kilometre Array, SKA, in Australia and South Africa, are designed to map the faint 21 centimetre signal of neutral hydrogen. This allows them to directly observe the cosmic dark ages, charting how the universe transitioned from a fog of neutral gas to the transparent ionized plasma we see today, the epoch of reionization. By seeing how this cosmic fog lifted, they can provide independent constraints on the timing and efficiency of the first stars and galaxies, offering a crucial cross-reference to Webb's deep field images. Furthermore, experiments like the CMB-S4, Cosmic Microwave Background Stage 4, in the United States, are planning to remeasure the ancient cosmic microwave background with unprecedented precision. By meticulously analysing the tiny temperature anisotropies in the CMB, they can infer the initial conditions of the universe with exquisite detail. This will allow scientists to check whether the density fluctuations imprinted on the early universe, as seen in the CMB, are consistent with the rapid and abundant galaxy formation that Webb has observed. Any discrepancies could point to new physics at play in the very first instance of cosmic creation. Looking even further ahead, the next generation of space observatories promises to extend Webb's legacy. The Nancy Grace Roman Space Telescope, launching later this decade, will conduct vast surveys of the sky, mapping cosmic structure on an even grander scale and with a wider field of view, helping to trace how these early galaxies clustered and merged. Beyond that, mission planners envision telescopes like the Habitable Worlds Observatory, which will build on Webb's infrared capabilities to study not just distant galaxies, but exoplanets around faraway stars, searching for the chemical signs of life, and even more futuristic concepts such as space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, scheduled for the 2030s, could potentially detect the background hum of primordial black holes or the gravitational ripples from the mergers of early massive structures, offering yet another, entirely different window into the universe's energetic youth. Each new instrument, each new theoretical model, and each new algorithm adds another piece to this grand, unfolding mystery. Webb may have provided the initial spark, presenting us with the undeniable paradox of galaxies like JD's GS Z13-0, but it is the collective ingenuity of humanity that will illuminate the full chain of cause and effect. Step by step, photon by photon, we are constructing a more complete picture of cosmic evolution, revealing whether the universe truly built its structures faster than our current theories allow, or whether we are merely glimpsing a deeper, more intricate layer of physics woven into the fabric of reality itself. The journey to understand the impossible galaxy is, in essence, the journey to understand everything. It reminds us that the darkness between the stars is not emptiness, but history waiting to be understood, an open book of cosmic genesis. The James Webb Space Telescope, launched with the promise of peering into the universe's infancy, has delivered far more than mere confirmation. It has presented us with a profound cosmic paradox. At the heart of this paradox lies JADES GS Z13, a luminous, chemically enriched galaxy, observed when the cosmos was barely 320 million years old. Its existence is an impossible exhibit, a beacon of light from a time when the universe, according to our long-established models, should have been a much quieter, less organized realm. This single, defiant galaxy has become nothing less than a Rosetta Stone, providing crucial insights that are simultaneously forcing us to reevaluate the fundamental nature of dark matter and the spectacular birth of the first stars, thereby challenging the very foundations of our cosmic narrative. Our intellectual journey through this enigma has illuminated the intricate web of challenges JADES GS Z13 poses. We've seen how its sheer brightness and inferred stellar mass at such an early epoch defy the slow, hierarchical assembly predicted by the lambda CDM model. The spectroscopic detection of heavier elements like oxygen and carbon within its ancient light further compounds the mystery, demanding a time frame for multiple generations of stellar birth and death that simply shouldn't be available within a few hundred million years of the Big Bang. This isn't a minor tweak to a timeline. It's a fundamental re-evaluation of the pace and efficiency of cosmic evolution. This profound anomaly has propelled us to re-examine the unseen architect of the cosmos, dark matter. The traditional cold dark matter model, with its passive gravitational scaffolding, struggles to explain the rapid clumping required to form galaxies like JADES G3 so quickly. This forces us to consider more dynamic possibilities, such as self-interacting dark matter, where particles occasionally collide and form denser cores, or fuzzy dark matter, whose wave-like properties could alter gravitational collapse. These theoretical shifts are not trivial. They require fundamental changes to our understanding of particle physics, transforming dark matter from a simple, inert component into a more active and complex player in the universe's formative stages. The impossible galaxy is essentially providing empirical evidence that we might need to redefine the dominant form of matter in the universe. Simultaneously, JADES GS Z13 has pushed us to rethink. To account for its rapid stellar assembly, we must envision a young universe unprecedented efficiency. This could imply the existence of supermassive population 3 stars burning furiously and dying swiftly to rapidly enrich the cosmos with heavy elements. Or perhaps the early universe was a maelstrom of violent galaxy mergers, triggering intense starbursts that consumed vast quantities of gas in explosive bursts of creation. The intense star formation rates hinted at by Webb's DataPaint True Stellar Furnace, operating at a level of efficiency and intensity far beyond anything observed in the modern universe. And then there's the surprising early reign of supermassive black holes. The presence of these colossal objects, millions or even billions of times the Sun's mass, in nascent galaxies like those Webb observes, forces us to abandon the idea of their slow, gradual growth. Instead, we are compelled to consider scenarios of direct collapse, where immense primordial gas clouds bypass star formation entirely to become black hole seeds, or incredibly efficient accretion processes fueled by the dense conditions of the early universe. This discovery suggests an intimate co-evolutionary partnership between galaxies and their central black holes from the very dawn of time, where these cosmic leviathans were not merely passengers but active shapers of galactic destinies. The profound interrelationship discovered here highlights that the impossible galaxy is challenging not just isolated phenomena, but the entire integrated system of cosmic structure formation. But the implications of JADES GS Z13 stretch even further. Venturing into the most speculative realms of cosmology, its existence forces us to critically examine our cosmic timeline itself. Could the universe's expansion history have been subtly different in its earliest moments, altering our calculations of distance and age? Could dark energy, the mysterious force accelerating expansion today, have had a variable strength in the past, allowing gravity to dominate more effectively in the early universe? And perhaps most profoundly, The impossible galaxy compels us to consider what time itself was like at the very beginning, leading some theorists to explore radical ideas of a bouncing universe or a quantum gravitational realm where time flowed differently. These are not just adjustments to existing models. These are calls to explore entirely new physics, hinting that the Big Bang, while a colossal event, might be part of an even grander, more cyclical cosmic narrative. The paradox dramatized by JD's GS-Z13-0 transforms it into a singular evidentiary exhibit, demanding a completely new understanding of the very fundamental laws that govern space, time, and matter. What JD's GS-Z13-0 unequivocally demonstrates, confirmed by rigorous astronomical due diligence and statistical validation, is that the infant cosmos was not the quiet, slowly evolving nursery scientists once imagined. It was a place of astonishing dynamism, turbulence, and creativity, almost from its very first instance. Galaxies grew sooner, stars ignited earlier, and black holes emerged long before anyone thought possible. Every new image from the James Webb Space Telescope deepens this mystery, enriching our understanding of a universe that is far more intricate and efficient in its self-organization than our previous theories allowed. The race is now on, a global, collaborative effort bridging astrophysics and particle physics. New analytical tools, powered by artificial intelligence, are sifting through petabytes of Webb's data, seeking hidden patterns and faint whispers from the cosmic dawn. Advanced computational simulations are testing radical new theories of dark matter, star formation, and even the geometry of space-time. Complementary observatories, from vast radio telescope arrays mapping the cosmic dark ages to future gravitational wave detectors probing primordial events, are adding new pieces to this grand puzzle. Each instrument, each theory, each discovery contributes to a collective tapestry, woven with the ambition to understand the full chain of cause and effect, from the universe's first instance to the vast, complex structures we inhabit today. Ultimately, the journey to understand JD's GS-13-0 transcends mere scientific inquiry. It is a profound philosophical reflection. It reignites a question as old as humanity. Why is there structure at all? If the universe organized itself with such astonishing swiftness and efficiency, perhaps creation is not a rare, delicate event, but an inherent powerful tendency of the cosmos itself. Some researchers now explore the idea of universal self-organization, where complexity arises spontaneously whenever energy flows through matter, whether in the fiery hearts of galaxies, the swirling patterns of storms, or the intricate chemistry of living cells. In this sense, the same fundamental principles that shaped the first stars and galaxies may still echo in the biological processes that led to life, and indeed, in the very firing of human thought as we strive to comprehend these cosmic wonders. Each photon captured by Webb from JD's GS-Z13-0 is more than just ancient light. It is a whisper from a time before there were eyes to see, or minds to wonder. These faint signals have travelled for billions of years across an expanding universe, carrying the indelible memories of a cosmos that was young, hot, and brimming with unimaginable possibilities. When we study them, we are not simply observing distant ancient galaxies. We are reading the preface to our own existence, decoding the primordial conditions that made everything, including ourselves, possible. We are deciphering the ultimate origin story. As the James Webb Space Telescope continues its groundbreaking mission, humanity stands at the precipice of a new kind of science, one that seamlessly blends meticulous observation with imaginative theory and cutting-edge computational power. Future telescopes will undoubtedly push our vision even further, perhaps eventually revealing the transition between nothing and something, the very moment when the universe first learned to create. Until then, every new image Webb sends home reminds us that the vast, seemingly empty darkness between stars is not void, but history waiting to be understood, a cosmic archive of Genesis. The telescope's golden mirror may hang 1,000,000 miles beyond Earth, but what it reflects back to us is profoundly human, an insatiable curiosity, an unwavering persistence, and an eternal hunger to know where everything truly began. It compels us to remember that the story of the cosmos is still unfolding, and together we are just beginning to read its most exhilarating, challenging, and awe-inspiring pages.